We're taking a peek at worksheet number 3 here, questions 4, 5, and 7. Starting with question number 4, it says, a 1,500 kilogram car traveling 100 kilometers per hour to the south collides with another car to the north. I'm going to draw attention to the south and north thing there. Heavier car continues to move south after the collision but slows to 25. How fast is the lighter car moving after the collision here? All right. There are a couple of things that are really important with this and that can lead to mistakes. One, probably the most important thing with these is the givens. Okay? A lot of people mess up on the givens. They have trouble with the subscripts, the 1, the I's, the 2's, the F's, and so on. Another thing that people mess up on are the signs when they go to plug them into the equation. That's just a careless thing, right? We can work past that. Third thing is rearranging the equation. That's just math skills that we have to work on. Okay, we can fix that. The first thing, which is our issue with the givens, that's probably the only real physics issue that we have with these questions. So let's focus on those givens here in this question. We have two masses, and we can name them whatever we want. We'll choose to name them M, I can say that, M1 and M2. We're going to say M1 is 1,500 kilograms, or 1.5 times 10 to the 3, and M2 is 1,200 kilograms. And we could reverse that, doesn't really matter. But we chose to call them M1 and M2. Now, V1, V2, they just have to be consistent with that, right? We have a velocity here that is 100 kilometers per hour. Whoops. 100 kilometers per hour to the south. We're going to make it negative because it's to the south. Is that going to be V1 or V2? Look, it's the 1,500 kilogram car traveling at that speed. 1,500 kilogram car is mass 1. So we're going to call that V1. Now, is that initial or final? Is that before the collision or after the collision? That's before the collision. So we're going to call that V1I. Okay, that is so critical to get that nailed. V1I. Okay, don't just call it V. Don't ever just call it V. It's V1I. Now, notice I left it in kilometers per hour. We'll talk about that in just a moment, okay? But right now, we'll just move on to the next one here. We have another velocity that is positive 100 kilometers per hour. What is that one? It says the 1,200 kilogram car. The 1,200 kilogram car is car what? Right? 2. So we're going to call that V2. Is that initial or final? Before the collision or after? Yeah, it's V2 initial. Good. Now the heavier car, which one's the heavier car? 1 or 2? 1. So that's going to be V1. Moves south after the collision. Okay, that's going to be V2F, or sorry, V1F, right? Is negative 25 kilometers per hour. And we're looking for the lighter car's velocity, V2, after the collision, V2F. Now, the reality is we need the speed or the velocity just before and just after in order that we have or I should say, in order that we have what's the word I'm looking for there? An isolated system with no external forces. If we're looking at 5 seconds before and 5 seconds after, there could be other forces that are coming into play here that we're not accounting for. We don't have an isolated system. Just before, just after, we have an isolated system, so conservation momentum is good to go here. Now, again, I haven't converted kilometers per hour to meters per second. If you did, that is absolutely fine to convert kilometers per hour to meters per second. Even if you've already done it, that's great. Okay, I'm just going to show you in a moment here why we don't actually have to do that in this question, why we don't have to convert to meters per second in this question. Pi is equal to Pf. We're going to say before the collision takes place, we have two objects. There's the momentum of the first one, right? Well, let's add that to the momentum of the second one, which is M2 V2I. That's the momentum before the collision takes place. What about afterwards? How many objects do we have after the collision takes place? 2. They don't stick together, right? They don't stick together, so we're going to say M1 V1F. That's the momentum of the first object after, plus M2 V2F, the momentum of the second one after. Now, if we were lucky here, the masses would be the same, which would allow us to cancel the mass out, right? They're not the same here. Okay, not a big deal. We just have to sub the values in. But what is the same throughout each term here? What is the same throughout each term here? Nothing? No? Anybody spot something that is the same? You're not looking for a number per se. Yeah. The units, including for velocity. Kilometers per hour, kilometers per hour, kilometers per hour, kilometers per hour. What cancels in this one? What cancels every time we have a conservation momentum problem? The units. That's why we can use kilometers per hour here as opposed to meters per second, because the units of kilometers per hour appear in every term. Does that make sense? If that confuses you, what should you do? Change it. Change it to meters per second. Okay, if it confuses you to not convert, then just convert, because it always works. Occasionally, like in conservation momentum, it also works to not convert, but it always works to convert. I'm going to go with kilometers per hour here just to save me the math of doing the conversion. Okay, but in the end, it's not a big deal. Okay, if it bothers you, or if you think not converting this time may get you out of the habit of converting, then just convert. Stay in the habit of it, right? Just means a tiny little bit of extra work for which we're not really worried about, really, because as we know, we have essentially unlimited time on our diploma exam. So we don't have to worry about running out of time because we converted units when we didn't really need to. William, question? Now, that's a good question. I gave the answer in meters per second here, because when I was doing my answer key, I actually converted to meters per second. This question doesn't specify what the answer should be in, meters per second or kilometers per hour. On a test, on an exam, on a quiz, it would specify kilometers per hour, meters per second. If it said kilometers per hour, and you converted to meters per second, you just have to convert back, right? If the answer said meters per second and you're doing what I'm doing now, you just have to convert to meters per second at the end as opposed to through the problem. So it doesn't really matter, but it will specify on a test or a quiz. You just have to pay attention to what it's specifying. Okay, I'm going to leave my answer key over here because my numbers are going to be different. I converted in my answer key. I'm not converting here. M1 is 1500 times V1I is negative 100 plus M2 is 1200 times V2I is positive 100. Okay, M1 is 1500 again. V1F is negative 25 plus M2, which is 1200 times V2F, which is, that's what we're looking for, I guess. Like, you could even, I don't know that there would be value in this. I don't think there would be any significant value at all, but even something like this, right? If it appears in every term, you can cancel it. 1500, 1200. You could, if you wanted to, cancel out those zeros, right? Make it 15 times negative 100 plus 12 times 100 plus or equals 15. You see what I'm saying there, guys? Whether it's units or a number or an exponent or whatever that appears in every term, if it appears in every term, you can cancel it. Conservation momentum is one of the few places that happens, though. All right, we won't cancel anything else. So 1500 times negative 100 gives me 150,000. This is 120,000. Oh, I don't know what that is. Somebody do this on the calculator because my answer key is different, like I said. 1500 times negative 25. Who's got that? Negative 37,500, thank you, plus 1200 times V2F. Let's combine these two numbers on the left-hand side. Negative 150 plus 120 gives me negative 30,000. All right, now we got to get rid of that 37,500. Over the last couple of days, I've seen a few people in a question like this dividing by 37,500. Do we divide by that? No, it's not. It's not multiplied by V2F, so why would we divide? Now, I saw some other people saying, oh, okay, I'm gonna subtract that. I'm gonna subtract that because it's added to the V2F, right? No, no, no. It's a negative value that's added. So what are we gonna do? We're gonna take it over by adding, right? We're gonna take it over by adding. Negative 30,000 plus 37,500 gives me 7,500. And then we're going to take the 1,200 over by dividing. 7,500 divided by 1,200 is going to give me somewhere in the range of, I don't know, 5 point something, isn't it? Kilometers per hour. 6.25, thank you. Now the units are kilometers per hour. How do we know they're kilometers per hour? Because that's what I used through the whole problem, right? The answer has to be in kilometers per hour. Now you want to convert that to meters per second. You're going to multiply that by, or sorry, not multiply by 3.6, but rather divide by 3.6. And I think when you do that, you end up getting 1.74 meters per second. Hey, how many people got 1.74 meters per second using meters per second throughout the whole problem? Go figure, you get the same answer, right? Of course you do. If you do it two different ways, but both correct ways, you have to get the same answer. If you don't, then we got a problem. Yep. Well, no, like it would specify on a test, like meters per second, kilometers per hour. It might, I don't know on a test. Like, yeah, it depends on the question, right? In this question, I'd be okay with either one because I didn't specify. But if it specifies, you just gotta, it's not a big deal. You just gotta be careful you do what it calls for, right? It would be an RTQ, ATQ, right? Read the question, answer the question. Yep.
So why can't you cancel out the masses for this?
You can't cancel out the masses because they're not the same. I got 1,500 and 1,200 kilograms. The units cancel because they're all in kilograms, right? So in other words, what we're saying is that if you're given the masses all in grams, that would have been okay because the units cancel. But the numbers don't cancel because the numbers are different. You have to have the same number in every term to cancel numbers. You have to have the same units in every term to cancel units. We have the same units, we don't have the same numbers. Yesterday, the problem that we did had, I think it was, I forget what was colliding. Something really light, like 0.06 kilograms or something like that. What was it? Oh, yeah, that's right. The ball that turned into a car. That's right. But they both had the same mass, M1 and M2, and that's why we were able to cancel that. Okay, does that make sense? Yep. Yep. All right, let's take a look at number, what was the next one? 6, was it? 5 that we need to go over? 4, 5, and 7 it was? Okay, 5 says 92 kilogram football player running at 6.5 to the north collides with a 85 kilogram player running to the south. What's the velocity of the 85 after the collision? 92 kilograms, we'll call it M1, 85 kilograms, call that mass 2 there. M1, mass M2. We have, here, let's say we have a velocity that's 6.5 meters per second. We have a velocity that is negative 6.00 meters per second. And then we have a velocity that is, this says the football player continues moving at 2 meters per second. He was moving north, so we'll assume that that means he continues moving north. Positive 2.00 meters per second. It's not good enough just to say V though. That's not good enough. Okay, the givens are so important in these questions, it's not good enough to just call it velocity. What velocity is it? This 6.5 meters per second. It says the 92 kilogram football player running at 6.5. The 92 kilogram football player is player number what? 1. So that's V1. Is that initial or final? That's V1 initial. That's how fast he or she is moving just before the collision. Okay, negative 6 meters per second. That's 85 kilogram football player running at 6 to the south. 85 is player number what? 2. So we're going to call that V2. Is that initial or final? That's initial, yeah, because it's before the collision takes place. Now, the 92 continues moving north. The 92 continues moving. So the 92 would be player 1, and that's after the collision, V1F. And finally, we're looking for V2F, the velocity of the 85 guy, he's number 2, after the collision. Now, just like in the last question and in every other question we've done with conservation of momentum, we say PI is equal to PF. And then we say, well, how many objects do we have? How many objects do we have before this collision takes place? 2 objects, M1, V1I. There's the momentum of object number 1 plus M2, V2I. There's the momentum of object number 2. Total momentum initial equals, how many objects do we have after they collide? Do they stick together? Nope. So we have 2 football players afterwards as well. M1, V1F plus M2, V2F. Masses cancel? Unfortunately, no, because they're not the same value, right? So we got to sub them in here. 92 times V1I plus 85 times V2I. 92 times V1F plus 85 times V2F. Get this number, combine them. Get this number, take it over by subtracting, because it's added on the right-hand side, right? And then divide by 85. We should get V2F equal to negative 1.13 meters per second. Is that okay? Do I need to show a little bit more detail in the calculation or the algebra here, or are you guys okay with that? Right, get the left side, and then subtract 100 and, what would it be, 184. Subtract 184 from it. Don't divide, because it's not multiplied by V2F. It's added to it, so it's got to be, come over to the other side by subtracting. Luke, welcome back. How come we can't cancel out the masses in this question?
Because they're different.
Right. Now, number 7, oh boy, number 7. Love this question. You're going to love this one. If you gave it an honest shot, you'll appreciate what I mean there, because it's a toughie. And if you manage to get it, actually, then you should feel a pretty good sense of accomplishment there, because that's a tough question. The problem with this one is that it involves relative motion, 2 different frames of reference. We have a situation where a person is holding a gun and firing the gun inside a train that is moving. That in itself is not a problem, but we're given a velocity of the bullet relative to the train, and then we want to find a velocity of the gun relative to the ground. 2 different frames of reference. The key here to this question, the fundamental key to this question, is recognizing that you have to be in 1 frame of reference. You have to be in 1 frame of reference. So you need to pick one. Okay? I'm going to pick the train as my frame of reference. Got it? So everything here in this question, until I get to the end, because I'm looking for the velocity of the gun relative to the ground, but everything throughout this question is going to be measured relative to the train. Got it? I'm going to write that down just so I don't forget. Relative to the train. Okay, we have a mass of a gun. It's 15.0 kilograms. We also have a mass of a bullet. I should have circled that, actually. Does it really matter whether you use grams or kilograms? It does and it doesn't. I could use either one, but I've got to be consistent, right? So that the units cancel. If I'm inconsistent with my units, they don't cancel because they don't appear in every term. I might as well go to kilograms since that's the normal standard units, but it would work if I went to grams as well. 50 grams is 0.0500 kilograms. 50 divided by 1,000 is 0.0500 kilograms. Now, we also have a kilometers per hour thing and a meters per second thing here as well. Either one would be okay in this situation, but I'm going to go meters per second because that's standard. That's normal. 75 kilometers per hour is going to convert to 20.833. Oh, wait a second. Wait a second. I'm not going to write that down yet. That's how fast the train is moving. Okay? The gun and the bullet are together before the explosion takes place, right? We're going to call that VI, the initial velocity of the gun-bullet combination. Got it? What is that relative to the train? 0. Like, you stand up, you're in a train, you stand up and you look around, but it's dark outside, so you can't see anything outside. You just look around inside the train. How fast is everything moving to you? It's not, right? You don't see people flying towards the front of the train. Everything's at rest relative to you, relative to the train. That make sense? So this gun and bullet initially, relative to the train, are at 0 meters per second. Relative to the ground, they're not. Relative to the train, they're at 0 meters per second. Now, V2F, we're given the velocity of the bullet after the explosion is equal to 350. Why 350? Well, because it tells me that's relative to the train, right? What am I looking for? V1F, the velocity of the gun. Now, we're looking for it relative to the ground. Understand when I solve for it this way, I'm going to get it relative to the train, but then I'll just convert it. And I'll explain how to convert it in a moment here. It's not that hard. So we're going to say PI is equal to PF. PI is equal to PF. Hey, listen, relative to the train, what's the initial momentum of the gun/bullet? 0. That's why, honestly, that's why I picked the train as my frame of reference so that I could make the initial momentum 0. If the ground was my frame of reference, and I could have done that, then I would have had to say there was a momentum, m total times v initial. It was a momentum before the explosion took place, before the gun was fired. M1 V1F plus M2 V2F. Now, mathematically, this is pretty straightforward. M1 is 15 times V1F is, that's what we're looking for here, plus 0.0500 times V2F is 350. Okay, solve this, take it to the other side by subtracting. When I do that, I get a V1F here, a V1F of negative 1.16667 meters per second. Okay, what have I just solved for? The velocity of the gun relative to the train. So picture this. You're in a train that is at rest. You fire the gun, the bullet goes forward at 350 meters per second. The gun goes backward at 1.16 meters per second. You're in a train that's moving. You don't know that. If the train is moving at a constant speed, you wouldn't know. The bullet goes forward at 350 relative to the train, and the gun goes back at 1.17 relative to the train. Now, how fast is it moving relative to the ground? Because that's what we're looking for, right? If you remember from Physics 20, when we did relative motion stuff, whenever you want to find the relative velocity, you have to add vectors together. Let me give an example. A nice, easy math example here. Go to the airport, you see these moving walkways, right? You guys know what I'm talking about? I always kind of like laugh when I see them because like you got like 3 kilometers to walk to get to your gate. Sometimes, maybe not quite. A long way sometimes, right? But then you're walking up and you see this moving walkway that saves you like 30 meters. You get on it and, oh, I don't have to, I can stand there and let it take me 30 meters. But you still have to walk like almost the whole way. But yet, everybody still goes on them, right? Because it's, I don't know, because it's fun, whatever, entertains you, whatever. The only problem is, like, I don't know, seems like whenever I want to go to a store, like the little convenience store there that sells the snacks and the magazines, it's like right in the middle. It's always right in the middle. It's like, so then I have to get on the moving walkway, go all the way down, and then come back, walk back to it. Anyways, let's say that clock on the wall is the store. Got it? See the clock on the wall? That's the store. That's the store. It's on the ground. It's at rest, right? The moving walkway is going this way at 2 meters per second. The walkway is moving this way at 2 meters per second. Got it? I have the ability to walk at 3 meters per second. Got it? I can walk at 3 meters per second. Right now, I'm walking on the ground at 3 meters per second. I get on that walkway. I can move relative to that walkway at 3 meters per second. What if I walk this way at 3 meters per second? What is my velocity relative to the moving walkway? 3. What's my velocity relative to that store back there? 5, right? Hey, you ever done that? You're walking on it, it's like, holy cow, moving fast. Like when you look off at the ground or the store there, right? What if, I do this sometimes too. It's more fun on escalators though, because it's harder. You go backwards, the opposite way. So the walkway is moving this way at 3, and you decide you're going to go, sorry, the walkway is moving this way at 2. You decide you're going to move this way at 3. What's your velocity relative to the walkway? 3. That's how fast you can walk on whatever you're walking on. What's your velocity relative to that store? 1, or actually -1, right? How did I find my velocity relative to the ground? I added the two vectors together, the 2 and the 3, or the 2 and the -3. Got it? Okay, so how do we find, let's go back to this question now. How do we find the velocity of this gun relative to the ground? Well, we add the velocity of the train, which was 20.833 meters per second. Right, that was 75 kilometers per hour. We add the velocity of the train, which was like the velocity of the moving walkway, right, to the velocity of the gun relative to that, which was like the velocity of me on the moving walkway, the velocity of the walkway plus the velocity of me, the velocity of the train plus the velocity of the gun. This is going to give me the velocity of the gun relative to the ground, just like it gave you a minute ago in my analogy, the velocity of me relative to that store that was off to the side. Okay, we do this, it ends up being 19.666 meters per second, which we're going to round to 19.7 meters per second. Did that make sense? That's a hard question. If you didn't get that, that's okay. My hope for you right now is that it makes sense to you after we've gone through it. Not necessarily that you got it, but that it makes sense to you after we've gone through it. I'm going to do one more example now, and then that'll be pretty much it for us for the day. This is example number 4, and unfortunately, this is not on your example sheet. Somehow I missed putting this on your example sheet. So I'm going to ask you either to copy this down or to snap a photo of it or something so that you've got this, okay? We are also missing a little bit of data on this. It should say a 1,000 kilogram car traveling east at 20 meters per second collides with a stationary 1,200 kilogram car. They lock together, then they hit another 1,200 kilogram car at rest. They had 3 cars now locked together and head off as one. I call this a progressive collision. The document that I gave you at the beginning of the year, it was called Physics 30 and 13 pages. It had all these little tidbits of stuff on each topic you needed to know. Under topic 15, conservation of momentum, one of the things was progressive collisions. That's just my name for this. Okay, if you talk to somebody from Foothills Composite or a school in Calgary, They're going to have to do this stuff too, but they're not going to necessarily call it what I call it. But they should know what you're talking about in terms of the concept. If they go to class, because we know how important that is, right? It's like a domino effect, right? It's like a domino effect. Car hits a car, then they hit another car. You've seen this before, right? It's that collision on the highway in the snowstorm when one car hits another car, and then they hit another one, and then they hit another one. Before you know it, it's a 47-car pileup in Olds or something in a snowstorm. Yeah, exactly. Going into Calgary there. How are we going to tackle this? Any ideas? Before I write down any givens, I want to look at how I'm going to tackle this. Any ideas? Yeah.
Instead of like the same, like
Okay, so like conservation momentum.
and then you have like P1I, P2I.
Yeah.
Yeah.
So how would I do that though? Like in one equation, all at once?
No, you'd spread it out, but like every time the car's hit,
Okay.
you
Oh,
have like the same mass.
okay. I think I know what you mean here. Let me clarify, and then you can tell me if that's what you meant or not. Okay. So I think what you're saying is that we look at collision 1. There's two collisions. We look at collision 1 with a PI equals PF. In fact, we'll call it, instead of PI and PF, because there's two collisions here, let's call it P1 and P2. Does that make sense? Okay. And then we look at the second collision where the momentum from the first one, the final momentum for the first one, becomes the initial momentum for the second one. So P2 equals P3. Is that what you meant?
Yeah.
Is that what you're going to say? Okay, so if P1 is equal to P2 and P2 is equal to P3, isn't P1 equal to P3? Right? So why can't we just look at this as one big thing? Guys, this absolutely is correct. You can absolutely do this to find the final velocity in the first collision, which becomes the initial velocity in the second collision, which we can use to find the final velocity in the second collision. Absolutely. But it's two calculations. If you think about this, if P1 equals P2 and P2 equals P3, then P1 is equal to P3. That's the way I'm going to treat this. Okay, I'm going to say Pi is equal to Pf. The total initial momentum here, the total initial momentum is M1 V1I plus, what's the momentum of the second car? What is it? Yes, it's 0 because it's at rest. What's the momentum of the third car? 0 because it's at rest. The total initial momentum is equal to M1 V1I. What's the total final momentum equal to? M total, because they've all stuck together, times Vf. Think about that. At the end of the problem, this is the momentum you have. At the beginning of the problem, this is the momentum you have. The law of conservation of momentum says the total momentum remains the same as long as you have an isolated system, right? So if we can assume this is an isolated system, then it doesn't matter what happened in between. The initial momentum will be equal to the final momentum regardless of how many collisions took place in between. Does that make sense? Does that make sense, everyone? Now, in the end, you can still do it this way, right? You can still do it this way. It's absolutely fine. The only problem that I would say with this, and it's a small one, it's only a small one, is that the more calculations you do, the more chance you have of making a mistake. If I can do one calculation and get an answer, then it reduces the probability of me making a mistake by a factor of 50%, right? This doubles my chance of making a silly mistake. But as long as you can avoid that, okay, it's still correct, and you'll still get the right answer. M1 is 1,000 kilograms. V1I is 20 meters per second. M2 is 1200. V2i is 0. M3 is 1200. V3i is 0. So the total initial momentum is due just to this object. Now, the total mass is 3,400 kilograms after the collision takes place because they've all stuck together. Sorry, after the collisions, both of the collisions have taken place because they've all stuck together. Times Vf, the final velocity of all three. The total initial momentum is equal to the total final momentum, regardless of what's taken place in between, as long as the system is an isolated system with no external forces. So let's do the math here. 20 times 1,000 is 20,000. 3,400 times Vf. 20,000 divided by 3,400 is 5.9 meters per second. Now, logically, we had one car supplying all of the momentum to this system. We have three cars taking all of the momentum away. The velocity of the three-car combination afterwards should be less than the velocity of the one car before the collision, right? Make sense? Less mass, more velocity, more mass, less velocity if the momentum is remaining the same. Got it?